Okay, so last time we were discussing about locality sensitive hashing algorithm that and using which we saw solution of approximate near neighbor problem. So we'll do a quick recap, and today we'll see some more like kind of specific instance of locality sensitive hashing algorithms. So I'll just do a quick recap of what we did last time, and then we'll see some specific examples of locality sensitive hashing algorithm. So essentially, so this locality sensitive hashing is essentially a family of hash functions. It's called a hash family, say H, that consists of some functions, and we call it R, CR, P1 and P2 sensitive. If for any pair of point P and Q belonging to our data set X, so if distance between P and Q is say at most R, then probability that hash value of both P and Q is same is with probability at least P1, and if distance between P and Q is more than C times R, then probability that H is at most P2, where P1 is much larger than P2 and C is some parameter greater than 1. And how this hash function help us to solve approximate near neighbor problem? Any idea? So basically using this hash function, we can design several buckets and we can group points into those buckets, and using the property of locality sensitive hashing function, it is guaranteed that similar point will go in the same bucket with high probability, and dissimilar point will go in the same bucket with very small probability. So essentially, once we get the query point, we'll see in which bucket it falls. And now our search space is reduces to the points belonging to that bucket only. So we don't need to compare the similarity or distance with all the endpoints in the data set. So basically, using this hash function, we design several buckets. And each bucket ID so is of size k, and we stack LSH buckets. This is L stack of buckets. So essentially, ID of a bucket is concatenation of k such hash functions. So this bucket ID is, we call it as phi as a GI of P, suppose, and it is HI1 P, HI2 P, HIK P, and so on. So basically, we sample k hash function from this hash family, and basically and concatenate the corresponding value, right? So all the buckets in this row, say for example in this row, is identified by say g1 of hash function g1. All the buckets in the second row are identified with another hash function, say g2, and so on, right? And based on the values, specific values of these things, basically different buckets are generated, right? So is this point clear to everyone? Now, if we follow this strategy, so what is the guarantee that we get? So we get the following guarantee. So
Sir, sorry,
yeah,
sir. Can you just explain that concatenation part again, please?
okay. So basically, we sample say k hash function from this hash family, say h, right? So suppose that function is say h I1, h I2, and h ik. We just concatenate. So basically, here we are designing a vector of dimension k, right? And this bucket ID is that vector of dimension k. So is this clear?
So that hi1 and all these all are again an individual hash function, right?
Yes. So these h I j, for example, are randomly sampled from this hash family h. Okay. So basically, to generate say first layer of buckets, we sample k hash functions from h, and suppose they are h1, hi1, hi2, and hik, and basically we just concatenate them together, and so accordingly we define functions as g. So basically this row of bucket belonging to this row are identified by this hash function g1, right? Similarly g2 and so on.
Sure, thank you.
Okay.
Another thing is also that like inside that one single bucket. So this
Yes.
is what you are talking about group, the row. But in that,
Yes.
the first one also something similar needs to be done, right? To generate the hash code of that bucket.
Yes. Yes. Okay. So maybe so suppose for example say our say k is 3, right? So this row, say first row, maybe it's h11, h12, and h13. So these set of hash function are defined our g1, which defines the first row of this thing. And now for a particular bucket, so suppose for example say h11 say take value 2, hi2 take value 3, hi3 may take value 5, for example. So this is id of some bucket, say 2, 3, and 5, right? So any point whose value hi1 is 2, h11 is 2, h12 is 3, and h13 is 5 will be mapped to this bucket, right? Similarly for this maybe it is a 1, 2, and 5. So basically ID of this bucket is 1 to 5. ID of this bucket is determined by three-dimensional vector which is 1 to 5. And all those data points whose corresponding H11 and H12 and H13 are 1, 2, and 5 respectively will be mapped to this bucket. And that's all.
Yeah. So then why we need this G1 hash function itself? Because what I understand is like, so similarly for the second row, there will be H2 1 and H2
Mhm.
2, something similar, right? There will
Mhm.
be a different hash function for the
Yes,
stack,
yes,
whatever we have said, L1 stack and
yes,
L2 stack.
yes,
So the
yes,
hash
yes,
function will be different. So if
yes.
we iterate through all the hash function, so then I
Mhm.
can go to the corresponding bucket accordingly. So why I need a hash of the row?
Okay, so basically your question is why do we at the first place require concatenation of k such hash functions? Why one hash function is not enough? Is this what you want to ask?
No, that part I understand, like for each bucket concatenation of k hash function that is required. That part I understand, but what I'm not understanding is like the GIP, right? Which you said that it is a concatenation of the hash function across the row. Where you started actually, the
Okay.
G1 GIP.
So basically this row is, so G1 is corresponding to bucket in this row, right? And this G1P is just if we P some point, so P belong to some data point, and how we calculate in which bucket it will go. Right? So that is kind of specific instance of GIP, right?
Okay, got it.
Right. So this basically, so each say GI is basically take care of all the buckets in particular row, right? And the specific values of GI which we get after uh, computing GI for certain data point. So whatever value we get, then it maps to that particular bucket correspond in that given row, right?
Okay.
Okay. So for example, say G1 take cares of all the buckets in this row. G2 take cares of all the buckets in maybe the second row. GK take cares of all the bucket in the last row, right? And now we need to assign all the data points to one of these buckets. And how do we do assignment? We just compute the corresponding value. So this bucket ID is determined by k dimensional vector, and based on the values, we just value that we get after computing the hash value of the corresponding data point, we just map it to the corresponding bucket.
Sir, I have a follow-up question on that bucket key. So you have taken k equal 3, it's fine. But let's say I have taken a big number. There might be a case that it will collide, right? I mean, you can
Yes,
have a,
yes. Go ahead.
No, so that's what I'm thinking, like how, like if there is a collision, then what will happen? Like you'll have a same, the key will be same. I'm just guessing that.
Yes, so it is quite possible. In fact, this is what the purpose of this hash function. So the guarantee is that if 2 points are similar, so their corresponding G value should be same, so that they basically map into the same bucket. And this is what we want, right? So we want similar point to fall in the same bucket.
Okay. So you're saying that let's say a number came 35. So we need to, have hash like H11, H12, H13 individually, and it
Mhm.
so that it will automatically fall into a corresponding bucket. Is my understanding
Yes,
correct?
yes.
So you're saying that any close to that, let's say 37 comes in, so that will fall approximately the same bucket, right?
Yes.
Nice. Thank you, sir.
Okay, so now the thing is, how should we
Sir,
choose K and L? Yeah, any more questions on this? Yeah,
yes, sir.
because this is settle point. Yeah, so
Sir,
yeah,
I just want to ask, like, the number of buckets in a row would be determined by P, right? The number of P, like how many inputs we have.
yes and no. Basically, suppose if your points are very similar, right? So
Yes,
maybe we do not require so many buckets, right? So it could be quite possible that all the points are mapped into say maybe 3 or 4 bucket, for example. So it
right.
depends how the points are distributed.
Okay, got it. Thank you.
So in one sense, you are saying that, I mean, it's like, what to say, any random you can take,
Random means
means approximately like, means how do we determine the number of K in that row? I mean, a number of buckets.
number of buckets. So like in practice, we can basically create bucket whenever required. Okay, so suppose you get first point, you get say some hash value 3, 2, 3, and 5. You generate a new bucket, assign it ID as 2, 3, and 5, and then map that point into that particular bucket. Suppose you get another point. For that, the bucket ID is 1 to 5. You create a new bucket and assign it to ID 1 to 5 and map that point into that bucket. and so on. So basically, whenever you required, you generate a new bucket, put that, assign that ID to it, and map that point to that particular bucket. So we are not generating all possible buckets to begin with, right? Because that may be overkill. So basically, whenever we get point whose corresponding this hash value is not belonging to the set of hash value that we have generated so far, then we create a new bucket and assign that ID to it, and then map that point to the bed bucket.
Okay, makes sense, sir. Thank you.
So one more question. So
Sure, sure. Yeah.
little bit confused with the convention. So if I take this diagram right as a matrix, so first box, whatever is that, it is 0, 0, and next is 0, 1. I'm just giving an example to.
Okay. Okay.
Okay. So if I am saying the G1, whatever you have mentioned, right? So that is nothing but 0, 0, right?
Yes. Yes. Okay. So you are saying this is, for
0,
example,
0.
this 0, 0, and this is a 0, 1. Yeah.
Yeah.
Okay.
So whatever G1 of P means, whatever you have written there, that is nothing but the 0, 0 bucket uh,
Yes.
data,
So
right?
okay.
Not
So
0,
in
0, right? It will be only
Yeah,
0.
yeah, that's what I
Sir,
got
it's the
confused
whole
because
row, right, sir?
I got confused with the second. Yeah, initially I thought of the same, but if I by writing the next line, right? If you have written like G1 of this thing is H1 of 1 and then H1 2, right? So
yes.
I got
Yes.
confused there. So could you please confirm whether it is 0 or it is 0, 0?
Where 0?
I
The
guess it is
entire row.
G0.
This is function. This is function.
Yeah, yeah, correct.
These are functions. Okay. So, and if we need to take some specific instance, we just put that point, and this is how the G1 of that point is calculated. So these are not 0, 0. So this is notation. So I think, so GI, so this is notation of function. Like this shows that this is a function GI, right? And this is calculated as HI1. This is a function, comma, HI2, HIK, right? So these are functions.
What is the parameter to that function? The dot
The
is
parameter
what?
input will be a data point, right? So P belong to X.
So that P here means
Data
exactly
point.
what is the uh, data point. So then it will correspond to only one bucket, right? 0, 0 bucket only.
Not 0, 0. Basically,
I mean,
the
I'm
value
just
that,
giving like, yeah, I mean, I'm not giving, I mean, I'm just showing that 0, 0 when I'm telling that I'm saying that that particular bucket which I am. So it will point to that particular bucket, right?
yes. And that
Or you
bucket,
mean to say entire row of the bucket?
no. Some particular
Yeah,
bucket.
that particular bucket. Okay, yeah.
Yes.
So actually, initially we thought it was row, then I got
No.
confused.
So
I
basically,
think
this
everybody
is,
thought also the same. That's what I
so
believe.
this
Yeah.
is row of buckets. So basically, you can think of this is one row which consists of, in which we are putting several buckets side by side, and each bucket ID is determined by basically the specific value that we get after executing these functions, right? So for example, this bucket ID is set 235, is 125, and so on, right?
Yeah. So GI of dot will be either 235 or 125.
Yes.
Okay.
But sir, again, you're saying G is a hash function, right? Which got formed with concatenation of H1,
Yes.
H2, and this one, right?
Yes. Yes. So what is your question?
No, I'm just getting confused. Like, uh, let's say any number comes in, right? So I'm just let's say how if you're trying to find G of I mean basically I want to find out where that number will fall into, right? That's what our
Okay.
target is, right?
Yes.
So we will
Okay.
be calculating HI1, HI2, and HIK. Then you're saying that whatever the key it will generate, just uh, I mean, enter that one into that specific bucket.
Yes. So one second. Okay. So suppose we get say some point u, right? So this point u will be mapped. So first we'll see in which where it is located in the first row of buckets, right? So for that we'll calculate g1 of u, right? And suppose that value is say maybe 2, 3, and 5, for example. So in that case, you will be mapped to this bucket, right? And now we'll calculate G2 of u to see in which bucket it falls in the second row of buckets, right? So for example, this bucket ID is maybe 359. So again, you will be mapped to this bucket. Similarly, for all this row, we'll calculate the hash value under G, and whatever the value we get, we assign the point to corresponding bucket, right? And finally, we'll calculate GK of U, and again we map U to that particular, say this bucket, right? So every point is mapped to L buckets, one per each, one bucket in each row.
Okay, sir, understood. Thank you.
Right. So is this clear to everyone?
Yes, sir.
Okay. So now let's see what guarantee do we get. Okay. So there are two properties. Like so, suppose if there exists suppose Q is our query point. Right. So suppose we have our data set and we have mapped all elements of the data set to one of these buckets using the procedure that we discussed just now. And we would like to have the following two property, right? So if there exists a point, say X star in our data set, so D is our data set, right? Such that it is close to this query point, that is, say distance between Q and X star is smaller than R, right? Then what we would like to have, right? So suppose if there is some point in our data set which is close to query point, then what do we want? We want that at least in one of these rows, like either this or this or this, at least one of these rows, both basically Q and X prime should map in the same bucket, right? Yes or no?
Yes, sir.
Yeah. So then we want that for some I belongs to this L, say 1 to L. How to write it? So GI of X star is equal to GI of Q, right? Basically, both X star and Q should map in the same bucket. And suppose that this is possible for any I from 1 to L, right? And the second thing is, so all those points whose distance from say Q is large, there should not be too many of those points which map in the same bucket in which point Q is mapped, right? So that we don't end up computing the distance of Q with large number of points, right? So this first property says that, okay, if there is some point which is similar to Q, it is mapped. It should be mapped in the same bucket in which Q is mapped. And the second point we would like to have that there are not too many points which mapped in the same bucket in which Q is mapped, and there are not too many points which are whose distance from Q is large, and they are mapped in the same bucket in which Q is mapped. Right. So we'll just write that property. So there are at most 4L points, say X belongs to D, with distance Q comma X is more than C times R, such that for some I, gi of X is equal to gi of Q. Right. So this is what I have written, like all those points whose distance is from Q is large and they mapped in the same bucket in which Q is mapped, there are at most 4 such points. Right. So these two property we want, and we showed that if we let and if we set say L as n raised to power rho and k as log n upon log 1 by p2, then both 1 and 2 holds with probability 1 over 3. Right. So basically, if we choose L as say n raised to power rho and k as this, then 1 and 2 holds with probability at least 1 over 3. And it could be boosted. Basically, if you want this to be, say, maybe some large number, then accordingly you need to choose constant that is attached over here. And that is easy to do just by choosing the appropriate constant over here. Right. So this was the framework. And now we'll see some specific examples of LSH. Okay, so any questions so far?
How does P1 and P2 are chosen?
Okay, so that maybe we'll see once we get one example. Like,
Sure.
okay, so this is just a framework, generic framework. Okay, so we have seen signed random projection, and that so last time when we discussed about signed random projection, we viewed it as dimensionality reduction algorithm. So which can also be seen as LSH for cosine similarity or angular distance. So in SimHash, what was the algorithm that suppose we have say 2 points P and Q, we take an angle between them is theta, and we take say random vector r, and our hash function was HRP is takes value 1 if inner product of P and R is greater than equal to 0 and 0 otherwise. And okay, and SimHash gives the following guarantee that probability that H of P is equal to h of q is what?
Theta by pi.
1 minus theta by pi.
Oh, sorry. Yes.
Okay, so this is, yeah, so this is the guarantee that we get. Okay. Okay, so now we'll just try to put this this is signed random projection, or SRP or SimHash in this setting, right? Okay, so our LSH condition is if, say, angle between, say, so this is notation for angle between P and Q is smaller than theta, and if angle between P and Q is more than C times theta, then probability that HP is equal to HQ then this is this should be how much? At least 1 minus theta by pi, right? And this is at least 1 minus C theta by pi. Right? So this is using the same argument for which we proved this. Okay, and now we can take this as, say, P1 and this as P2. Okay, so what is the value of rho? So essentially, if we see this theorem carefully, so this is parameter rho, and in a way, it this rho gives a trade-off between say query time and size of the hash table. Right? Okay, so what is the value of rho here? Rho is log P1 by log P2. So log P1 is 1 minus theta by pi, 1 minus C theta by pi. So this is just some approximation. And log 1 minus s can be approximated by minus x. So basically just doing this Taylor series expansion, we can write this as minus theta by pi and C theta by pi. So this is roughly 1 over C. Okay. And so what is our query time? So query time is what? For a given query point, how many points do we need to compare? At most 4L, right? So So is this point clear to everyone? So just interrupt me if you have any doubts. So since we are computing distance with at most 4L points, right? So query time will be 4L, and basically computing the distance requires order D time. So it will be computing distance between two D-dimensional vector is of complexity order D. So it will be roughly order DL, right? And L is n raised to power rho, which is order D n raised to power rho, and rho is 1 by C. So essentially it is order D n raised to power 1 by C. So we'll see what is the interpretation of this. Okay. And size of hash table. So any idea like what will be the size of hash table?
Maximum of
Sorry.
maximum of LK. I mean LK.
Okay, so first we need to store the points. So for that we need dn, and we are in each row we are storing n points, right? So in each row here, in each row we are storing n points. Basically all n points are hashed for this row. All n points are hashed for this row. So basically there are L such rows, and in each row we are hashing n points. So just to store them, we need L
NL.
into NL space, right? N into L. So which is dn plus n, and L is n raised to power rho, which is dn plus n raised to power 1 plus rho, which is dn plus n raised to power 1 plus 1 by c, right? Now if we see these two terms carefully, so what is c? Any idea what is c here?
C is 1 by row.
Yeah, that is true, but yeah, like from by looking at these two statements.
Error.
Yeah, so C is basically C determines the region in which our algorithm don't provide any guarantee, right? So if C is large, then basically our query time will be small. So suppose if say C is 2, for example, right? So what will be the query time? So query time is order D root n raised to power half, right? And the size of hash table will be dn plus n raised to power 3 over 2, right? So basically this C in a way give us the trade-off between the query time and the size of hash table with respect to uh, basically the margin of error that the user can tolerate. Right. So is this point clear?
Sir, one question related to use of this. So related to the space, we are
Yes.
storing more than n
Yes.
items, right?
Yes.
So
Yes.
is that efficient? I mean, for example, if we use, let's say, a sorted array, we store a sorted array and calculate the distance to the incoming point,
Hmm.
for example, whatever error we are okay with, isn't that more efficient in terms of space? Uh, I'm not sure about the time. It might take on, but space-wise, I'm talking about more efficient, right?
Yes. So here basically, uh, basically this is used in those application where basically we have the points in the data set beforehand and we can pre-process them in the way we want. And the main challenge is to, once we get query point, we should be able to answer its closest point or similar point in very like kind of efficiently, right? So although, so that's the cost we are paying, like in order to get this is sublinear query time, right? So our query time is sublinear, but our space required to store the hash table is superlinear, right? So if we are okay to, in those application, if we are okay to have superlinear space complexity, but we are particular with sublinear query time algorithm, then in those application, this LSH mechanism can be useful, right? And you are
Okay.
saying shorting, then
I was talking about real valued, or just one-dimensional values.
hmm.
So that may not be the case for vectors.
Yes, yes, yes.
Yeah. Okay. Thank you, sir.
Right. So typically the sublinear query time comes at the cost of superlinear space required to store the hash table. So it can be used in those applications in which we can afford to use superlinear uh, space for to generate hash table. Right. So that's a good point. Yeah. Any other question on like whatever we have covered so far?
So that log P1 and P2 is that log of 1 minus theta by pi. So can you explain that how P1, P2 became 1 minus theta by pi?
Yeah.
What?
So by this property of SimHash, like if the 2 points, their angle is at most theta, then the probability that their hash value will be same is 1 minus, will be at least 1 minus theta by pi using this property. Right?
Yes, sir. Okay, and one more thing, like if it will be good if you can explain that SimHash, like exactly how we are getting theta by pi. Meaning I understand intuitively, but if you can just throw some light on that.
Okay. So basically the idea is we take a random hyperplane, right? R. So suppose vector R consists of value say R1 to Rd, where each Ri is sampled from normal distribution with mean zero and unit variance. So basically we are taking a random hyperplane, and if that random hyperplane uh, basically separates P and Q, then the hash value of P and Q are different, right? So then basically if random hyperplane separates P and Q, then inner product of P and R will be of different sign than inner product of Q and R, right? And the probability that their hash value is same, basically this random hyperplane is not able to separate point P and Q is 1 minus theta by pi. right? So basically, in a way, we have 2 points P and Q such that their angle between them is theta, and we are taking a random hyperplane. So what is the probability that that random hyperplane separates P and Q? So that is theta by pi. And what is the probability that their random hyperplane is not able to separate P and Q? Is 1 minus theta by pi. So this is what is captured in this expression.
Yeah, thank you, sir. And if it is dividing, that means they are separate. If it is not, they are in the
Yes,
same. And how
same side.
many? So this generation of this hyperplane, right? So that will be also random. Like we will generate random RT planes
Yes,
and
yes,
apply all these points across every all the. Uh, uh, Meaning we will either, meaning sometimes we can get one. If it is matching, it can be true or false that way. Then
yes.
what can happen is, like, if I have like 100 hyperplanes, and
Mm.
for each, if I am applying, there might be some plus, meaning matching or not matching, right?
Yes, yes, yes.
So, and based on that, can I decide the hash code of that particular like
Yes, yes.
those 2 points? I'm just thinking about the application side, how to implement this. So that way, like
So basically generating this hash function is nothing but generating a random vector, right? So suppose you generate a random vector like this. So this essentially this random vector R captures one hyperplane. You generate another random vector that will capture another hyperplane, and like consequently the hash functions like this.
got it.
Okay, and again you can just put it, so this H in this framework, right? Again you can generate concatenate k such hash function and define G and repeat it L times, right? So this is generic, and the SimHash is one specific instance where our input is real valued vector and similarity is angular similarity, and H is this SimHash, right? And this guarantee will follow, right? Any questions on this? Okay, so we'll see one more example of LSH, that is LSH for Euclidean distance.
Sir, how do we generate the bucket IDs using SimHash here in this?
Again, like in case of SimHash, the bucket ID will be binary, right? So SimHash bucket ID is either, like, for one hash function, so it is either 1 or 0. Like if you concatenate, say, k such hash functions, in this case, like this, so it will be a string of binary string of length k.
Oh, okay.
Right? So it will be a binary vector. So each bucket will be identified by binary vector of size k. Okay, so now let's focus on LSH for Euclidean distance. So again, in case of LSH, we would like to have some hash function, using which, if there are 2 points which are similar, basically their Euclidean distance is small. So with high probability, their hash code should be small. Hash code should be same, and if their Euclidean distance is large, then with high probability, like with very small probability, their hash code should be same. Right. So any idea, like, what can we do about if we need to come up with LSH for Euclidean distance?
Yes, probably the same idea of hyperplane and just throwing some
Yes.
idea.
So
So basically the distance between feet on that particular plane and the distance between few to that plane, based on that, something we can decide.
So
Uh,
yeah, roughly along the same line, but there could be some subtlety. So suppose in this case, in case of SimHash, so suppose we have say two data points, say P and Q, right? So it is possible to generate 2 points such that their angle is very small, but their Euclidean distance is very large, right? So this is a theta is very small, but their Euclidean distance could be very large. It's very large, right?
yes, sir.
So yeah, so the idea is a bit unintuitive, and of course that's why it's appeared in very, like kind of very good venue. So basically the idea is, so suppose we have 2 points P and Q. Okay. So we take a random line. Suppose we are taking this as our random line. And we are projecting our point to this random line. So suppose this is a random line R. Again, can be basically this R is generated. This is R1 to RD. And each Ri is sampled from normal distribution with mean 0 and unit variance. And we are projecting this point on this line. So this is projection of P on line R. And this is projection of Q on this line R. Right? And now, so but basically here, if you see, so our hash value should be some, basically here, our hash value should be some discrete number. So this should be some discrete number, some integer valued number, right? So then only we can assign it to some bucket ID, and we can compute the basically bucket ID and compare uh, the corresponding ID with in new data point and do the mapping, right? We cannot afford to have this as some real number, so maybe 0.99 and so on, right? So is this point clear to you? So we want this bucket ID to be some discrete value, discrete or integer value, in fact positive integer value, right? Then only we can do this, we can assign it to some particular bucket and compute the ID of a data point, and based on the value we can assign it to some particular bucket, right? So does this point make sense to you? Right? Okay, so now what we do here, yeah, so this is a bit not so intuitive. We just split this line segment R into basically blocks of size W. So these are basically blocks of size W. Right, and our hash function is h of p. So again, basically we take dot product of p with r, this random vector, right? And we add a random number b and divide it by this w and take the floor of it, floor or c, whatever. And w is width of this quantization. So basically the idea is we take a random line, a random hyperplane R, project our point P and Q on that hyperplane and see whether they are falling in the same block or not, right? So this is, you can think of this is as say maybe first block, this is second block, and so on, right? And we are adding some random offset B, which is sampled from say 0 to W. So here the intuition is, if say distance between point P and Q is small, then they will fall in the same block, right? So here you can see the distance between P and Q is large. So they are falling into different block, like P is falling in this block where Q is falling in this block.
And it will be the same, like we will, yeah, I think you have already written. We will have multiple lines, right? And then do this.
Yes. So this is one specific hash function. And again, you can put it in this framework. Just repeat it k times and for each row and repeat it L times and choose this value of k and L like this. Then you get this guarantee. So this is just specific instance of for Euclidean distance.
And that B meaning is some kind of bias, like what is that B means?
B is some you can think of. So basically, the idea is take a random line, project the point P and Q, and basically divide this line into block of size W, right? And we are just adding a random offset, right? So that basically just from where we are start creating the block. So this is just a random offset for that. Okay, but although like, is it intuitive? Like if P and Q, their Euclidean distance is small, then most likely they will fall into the same block. Right? And
Do we keep W constant for all hash functions or do we change it, sir?
yeah, so this hash function is basically determined by R. Yeah, so R and B. W is kind of fixed basically, and it also not fair. So suppose in first case you choose W as say some large, then basically choose the W of value of W is large, then basically points whose distance is large, they can get the same hash value, right? So W is fixed. All we choose is different B and R.
I mean, so if the hyperplane is very far from, I mean, the angle is very high compared to P and Q, and if we keep W fixed compared to a hyperplane which is close to P and Q, in the farther one, they'll fall in the same bucket, right, sir? So that's why I was
Yeah.
asking, do we change? Okay, okay. I think we should, yeah, I got your point, sir.
Yeah, otherwise, like if we can take very large value of W and everything will fall in the same, we'll get the same bucket ID. Right. So in practice, I think like choosing W as a 4 provide good results. So like in papers, you can see like different plots corresponding to choosing different values of B and R and how the collision probability is going on. Okay. So, okay, so I'll just write one expression, which is the probability of collision. So suppose if we denote, say for two data point P and Q, suppose I'm denoting that their L2 distance as say P minus Q as say phi, then probability of HP is equal to HQ. So this is not so straightforward, but not that involved as well. Like it's 0 to W, 1 by this phi, the distance. So it's inversely proportional to the distance, and f of t by phi 1 minus t by W dt, where f is PDF of Gaussian. Gaussian distribution. Right. So if we choose this hash function, then the probability of collision follows this expression. So this may be a bit involved, but it's intuitively it is inversely proportional to the L2 distance of P and Q. Like so, if the L2 distance of P and Q is large, then the probability that their hash value will be probability that their hash value is same will be large.
So probability will be small, right? It's in the denominator.
Yes, yes, sorry, yeah. So if the L2 distance is large, then the probability that their hash value is same will be small, right? Because it is inversely proportional to it.
But what is T here?
What is what?
T.
T is basically a parameter on which we are doing integration.
So can you explain once again this Gaussian distribution video?
Yes, sorry.
Can you explain once again this formula, the integration part?
So yeah, so this F is PDF of Gaussian distribution, and this is 1 minus T by W.
Why you have chosen the PDF of Gaussian distribution?
Because we are choosing this line with whose each coordinate is sampled from Gaussian distribution.
Oh, okay. Yeah. Okay.
Yeah, so proving this is, yeah, that's what I'm saying. Like, it's not very difficult, but not very straightforward. So I would like to skip it. And if you want, you can just go over the notes and verify it. Right. And again, using similar type of analysis like this, it is possible to show that again, rho will be say 1 at most 1 by C and so on. Basically just put instead of here R and CR and calculate P1 and P2 and calculate log P1 ratio of log P1 with log P2, and you can get rho, and finally you'll get C. So that calculation is somewhat involved, not very involved. Right. So the main idea is to convey like what is the hash function for Euclidean distance. Right. So, but intuitively, I hope you'll be able to like convince yourself that if we choose this hash function like HP as like this hash function, then probability that hash value of two data points P and Q is inversely proportional to their Euclidean distance. Right. So I hope this thing is clear, but exact calculation of probability comes by this expression. Okay, so I think we can take a break here now. So